Welcome to Talk Tensors. If you're listening, you probably want to keep up with the bleeding edge of machine learning research.
Yeah, especially the academic side.
Exactly. And today we've got a paper that's really interesting. It digs into something critical for AI-generated images: semantic watermarks.
Right, those hidden IDs you can embed in images from diffusion models.
Yeah, and specifically, this paper looks at the cryptographic side of one method, Gaussian shading. It asks, are we actually using the crypto correctly?
Which is, super important. As these models get everywhere, we need ways to track where images come from, prevent misuse.
So this paper, the title is Towards a Correct Usage of Cryptography in Semantic Watermarks for Diffusion Models. Quite a mouthful.
Yeah, but it gets right to the point. They're saying, look, the way Gaussian shading was initially set up cryptographically, maybe not totally solid.
Okay, so they found flaws.
Flaws, or maybe underspecified aspects. They propose a much more rigorous security proof and basically give guidelines on how to use the crypto properly to make these watermarks genuinely secure and crucially undetectable.
Right, because if they're detectable, that kind of defeats the purpose.
Or removable or forgeable. Yeah, it undermines the whole idea of using them for, say, copyright or tracking provenance.
Before we dive into Gaussian shading specifically, maybe give us the quick overview. Semantic watermarking in general, what's the basic idea?
Sure. So the kind we're talking about, inversion-based semantic watermarks, they work by tweaking the initial random noise that a diffusion model starts with.
The latent noise, right?
ZT, exactly, ZOT. And the cool thing is you don't usually need to change the main diffusion model itself. The watermark gets baked in during the image generation process.
Okay, so it becomes part of the image's fundamental structure, in a way.
You could say that. Now, there are broadly two flavors of these methods.
Okay.
First, distribution-changing ones, like a tree ring or ring ID. You might have heard of them.
Yeah, vaguely.
They actually change the statistical properties of that starting noise, often by adding sort of fixed patterns in the frequency domain. Think of it like adding a very faint, specific kind of static.
So if you know what frequency pattern to look for, you could potentially spot it?
Precisely. Then there's the second category, distribution preserving methods.
Like Gaussian shading?
Like Gaussian shading, and another one called PRC. These try not to change the overall statistical feel of the noise. They keep it looking like standard Gaussian noise.
So how do they embed the watermark then?
They use cryptography. They use crypto to subtly steer the sampling process from that noise distribution, rather than changing the distribution itself.
Ah, okay, more subtle. And this paper zeroes in on Gaussian shading's crypto.
Right. Gaussian shading uses crypto primitives, think basic building blocks like stream ciphers, to create a pseudorandom sequence. And that sequence influences how the latent noise is sampled.
And the paper found issues there?
Yeah, several points. The original paper wasn't super clear on which specific crypto primitive should be used. The proof they gave for undetectability or lossless performance was a bit shaky, especially if one user generates lots of images.
Uh-oh.
And they didn't really discuss the implications for key management, which, as we'll see, is a big deal.
Okay, let's talk about the crypto element. Stream ciphers, like Chachwanier mentioned, how do they fit in?
Okay, so imagine you have a secret key, right? And a public number called a nonce, which should ideally be used only once per key.
Okay, key and nonce.
A stream cipher, like Chachwani, takes that key and nonce and spits out a long stream of bits that looks completely random. This is the key stream.
Like a one-time pad, almost?
Sort of, yeah.
Yeah.
You then take your actual message, in this case, like a user ID you want to embed, and you combine it with this key stream, usually using XOR.
Oh.
The result is the ciphertext. And because the key stream looks random, the ciphertext should also look random. That's key for making the watermark undetectable within the already random-looking latent noise.
And to get the message back.
You need the same key and the exact same nonce. You regenerate the key stream and XOR it with the ciphertext again. Boom, original message pops out.
And the security relies on that key stream being unpredictable without the key.
Exactly. And a good stream cipher means even flipping one bit in the key or nonce totally changes the entire key stream, unpredictably.
Got it. So how does Gaussian shading actually use this to watermark an image? Walk me through the generation.
Okay, so the service provider, say, assigns a user a random ID. Let's call it M.
Okay, M's of the message.
Right. Now, for a given text prompt, the process starts by sampling the initial latent noise, ZOT. But instead of just picking random Gaussian values, Gaussian shading modifies things. First, they usually replicate the user ID multiple times.
For error correction, like if the image bit's compressed or something?
Exactly. So you get replenum. Then this replicated ID gets encrypted using the stream cipher with the secret key K and a nonce. That gives you the ciphertext C.
Okay, encrypted replicated user ID.
Now, here's the clever bit. This ciphertext say-so is used to steer the sampling of ZT. Imagine the standard normal distribution, that bell curve. They divide it into bins or sections. The bits of the ciphertext Cs basically tell the sampler which bin to draw the random noise value from for each dimension of the latent vector.
Whoa. So the encrypted message directly guides the random noise selection.
It guides it, yeah, subtly nudging it based on the encrypted ID. The final watermark latent, let's call it SOC, is then fed into the normal diffusion model generator G, and out comes the watermarked image X.
Okay, that's complex, but I think I follow. How do you check if an image has this watermark? Verification.
Right. So you take an image you suspect is watermark X. You first run it through an inversion process I to try and estimate the original latent noise it came from. Call that OT.
An estimate, because inversion isn't perfect.
Correct. Then you apply an inverse sampling process I. This essentially looks at the values in OT and tries to figure out which bins they most likely came from during the guided sampling. This gives you an estimated ciphertext.
Trying to reconstruct the encrypted message.
Yep. Then you take S and decrypt it using the secret key and the nonce you think might have been used.
Yeah.
Finally, you apply the inverse replication, the error correction, ROPLO, to get a candidate user ID.
And then you check if mem matches a known user ID.
Exactly. You compare mem against your database, usually allowing for a few errors, using some threshold. If it's close enough, you say, yep, this image was likely generated for user M.
Makes sense. Now, the paper talks about a stronger security proof using IND-CPA. Sounds intimidating.
Yeah, crypto names. Okay, IND-CPA is a standard crypto goal. It stands for indistinguishability under chosen plaintext attack. Roughly, it means an attacker can't tell the difference between the encryption of a message they chose and the encryption of, say, just zeros, even if they get to see lots of other encrypted messages.
Okay, so they can't distinguish real ciphertexts from fake ones. What's the dollar in IND-CPA?
The DOL signifies a stronger version, sometimes called real or random indistinguishability. The attacker tries to tell the difference between a real ciphertext and a truly random string of the same length. This paper argues that IND-CPA is the right security goal for semantic watermarks. It means the watermark is indistinguishable from random noise.
So if a watermark scheme is IND-CPA secure, an attacker looking at an image literally can't tell if there's a watermark hidden in the latent space or if it's just pure random noise, even if they've seen other watermarked images.
That's the ideal, yes. The paper formalizes this using a game standard practice in crypto proofs called priv-kendoi-kie. An adversary plays this game, trying to win by correctly guessing if an image is watermarked or just random.
And what did they find about Gaussian shading?
Here's the key result. Gaussian shading can be proven IND-CPA secure if the stream cipher underneath, like Chatzar, is itself secure. And this is the big one, if you use a fresh, unique nonce for every single image generated using the same secret key.
Ah, the nonce again. So reusing the nonce is the weak point.
It's a critical vulnerability, yes. If you use the same key in the same nonce to watermark multiple different images, even for different users or the same user multiple times, an attacker who can invert the images might see correlations or patterns in the recovered ciphertexts.
Oh, so?
Because the same key-nonce pair will always produce the same key stream. If an attacker inverts several images watermarked this way, the recovered values might share statistical similarities that wouldn't exist if truly random noise or different nonces were used each time. It breaks the randomness needed for indistinguishability.
Got it. So the secure way, according to this paper, is same key, new nonce for every single image.
That's the configuration they prove secure.
What does that mean in practice, though, for actually deploying this?
So the good news is this same key new nonce approach doesn't seem to hurt image quality or the variety of images you can generate. That's important.
Okay.
But the bad news is it's potentially very inefficient. Think about verification. If you used a unique nonce for every image tied to a single key, how do you check a suspicious image later?
You'd need to know which nonce was used for that specific image.
Exactly. Which means the provider would theoretically need to store every single nonce they ever used, linked somehow to the images or users.
That sounds bad. Like terabytes of nonces.
Potentially, yeah. And verification would mean trying to decrypt the recovered watermark, using potentially thousands or millions of stored nonces for that key until you find a match. It's a huge computational and storage headache.
Yikes. Okay, so secure, but maybe not practical at scale. How does that compare to other methods? You mentioned PRC earlier.
Right. The paper points out that PRC was designed partly to address this nonce issue. PRC manages to embed information about the nonce within the watermark itself, so you don't need that massive external database of nonces for verification. It makes deployment much more feasible while still aiming for similar security goals.
Clever. What about other key nonce setups for Gaussian shading?
Well, you could use a new key, new nonce for every image. That's also secure, IND-CPA secure, in fact. But it doesn't really buy you any extra security over same key, new nonce. And now you have the added complexity of managing tons of unique keys plus tons of unique nonces. Seems unnecessarily complex.
Right. More keys to store and protect.
And then there's the same key, same nonce approach.
Yeah.
Easiest to manage for sure. You just have one key and one nonce per user, or maybe globally.
But insecure, as you said.
Exactly. The paper argues it's not secure according to their definition because it's not nonce respecting. Plus, there's evidence it can actually degrade image quality and variety because you're essentially forcing the sampler to use the exact same cryptographic input sequence repeatedly, which might lead to repetitive artifacts or reduced diversity in the generated images.
Okay, so this paper really drives home that the crypto details, especially nonce handling, are absolutely critical for making these watermarks work securely and effectively.
Totally. It's a great example of how you can't just slap some crypto onto a system. You need to understand the security models, the proofs, and the practical implications. It's about getting the foundation right.
It really lays down a marker for what secure semantic watermarking should look like, cryptographically speaking.
Yeah, it provides a much more solid footing for evaluating and developing these techniques, which is crucial as we think about deploying generative AI responsibly.
All right, let's shift gears to our novel notions segment. Based on this deep dive, what kind of future research ideas spring to mind? Where could this lead?
Okay, well, the big practical hurdle we identified was nonce management for the secure same key new nonce setup, right? The storage and lookup problem.
Yeah, that sounded pretty rough.
So one interesting direction could be finding ways to generate the nonce deterministically but still securely.
Yeah.
Maybe you don't need a purely random nonce stored somewhere.
How would that work? Deterministic sounds predictable.
Well, maybe the nonce could be derived from, say, a combination of the secret key, or part of it, and some public or semi-public context, like a high-resolution timestamp of generation or a counter specific to the user, may be hashed together with the key material.
Ah, so the provider, knowing the key and maybe the approximate time the image was made, could recalculate a small set of candidate nonces to try during verification.
Exactly. Instead of storing millions of nonces, you just need the key and some logic to generate likely nonces based on context. You could use things like cryptographic hash functions, or PRFs, pseudorandom functions, to make it hard for an attacker without the key to guess the right nonce, but easy for the provider.
That could make Gaussian shading much more practical.
It could significantly improve scalability, yeah, making these nonce-based schemes viable for large platforms. The challenge, of course, is the balancing act.
Balancing what?
Balancing the predictability needed for the provider to reconstruct the nonce against the unpredictability needed to stop attackers from figuring out the nonce generation scheme or predicting future nonces. That's a tricky cryptographic design problem.
Makes sense. Okay, what's another idea?
Another thought is about maybe combining different types of watermarks. We talked about distribution changing versus distribution preserving. What about a hybrid approach?
Using both. How?
Imagine you embed a relatively simple, maybe less robust, distribution-changing watermark like a faint frequency pattern. This could act as a quick, computationally cheap first-pass check.
Like a canary signal. Is anything here?
Exactly. If that fast check flags a potential watermark, then you engage the more computationally intensive but cryptographically stronger distribution-preserving verification, like the Gaussian shading process we discussed, to actually identify the user.
So layer the techniques. Fast and noisy check, followed by slow and precise check if needed.
Precisely. It could give you the best of both worlds, potentially. Speed and broad detection from one layer, strong cryptographic security, and user ID from the second layer. Could make the overall system more robust against different kinds of attacks and more efficient for scanning large volumes of images.
What are the potential downsides there?
Well, you'd need to design it carefully so the two watermark types don't interfere with each other. Like, does embedding the frequency chunks mess up the subtle cryptographic steering? Does it hurt image quality more? And key management might get even more complex if you have keys for both layers. But it's an interesting architectural idea.
Definitely some cool avenues for future work there. It really shows this field is still evolving rapidly.
Oh, for sure. As always, these are just speculative ideas, food for thought.
Of course. But wrapping up, the main takeaway seems clear. Getting the cryptography right, especially things like nonce usage, isn't just an implementation detail for semantic watermarks. It's fundamental to their security and usefulness.
Absolutely. This paper is a strong reminder of that, highlighting those crucial trade-offs between security, how efficient the system is, and, the quality of the images you get out.
If you want to really get into the weeds with the proofs and the experiments, definitely check out the paper itself. We'll link it in the description. It's a great read on the rigorous work happening behind the scenes.
Yeah, essential stuff for responsible AI.
So thanks for joining us for this deep dive. It leaves us with a final thought. As these generative models get even more powerful and subtle, how do we ensure our watermarking techniques can actually keep up? Can they stay ahead of increasingly sophisticated ways to detect or remove them? Something to ponder.